Good evening. Hello, hello, hello. You guys ready to review some Freefall and Simple Machines? Yeah, you are. Yeah, you are. Alright. Should we just jump into it? Or do you have any over the top, whatever you want to call it, overarching questions before we start? And I forgot my water. I'll be right back. We're going to go through and look at each learning target. If you have a specific question about each learning target as we get to it, save your question. So if we're on a specific learning target and you have a learning target for one of the ones that is earlier, make sure that you wait until I get to that learning target, then ask the question, okay? Otherwise, you're going to get all confused. I'm going to miss the question, and you will not get it, or you'll just end up spamming chat, and that's annoying. Please don't do that. Okay. So we're looking at Common Assessment 4.2. This is our last Common Assessment for the semester. It is the second half of Unit 4, and we are looking at Freefall and Simple Machines, starting with AKS 8C, which talks about interpreting data to discover the relationship between mass and gravitational force for falling objects. Okay, so we're looking at free fall, terminal velocity, gravity, mass, and weight. So as we go through, we are going to be looking at the different learning targets for it. Okay. So, first learning target. I can explain the difference between mass and weight. This is very simple. Do you know what mass is? Do you know what weight is? We've done this plenty of times. You think that these words are interchangeable. Most people do use them interchangeably, but they are not interchangeable. They mean two completely different things. Mass is talking about how much matter you actually have, okay? How much matter you have makes up your mass, and it's measured in grams or kilograms or any other sort of prefix with grams in front of it or behind it. So weight deals with the force that gravity has upon your mass. Okay, so when we're talking about weight, we're literally talking about force grav, the force due to gravity. Okay, mass deals with how massive how much stuff you actually have, and weight deals with how your stuff is being for lack of a better term, being pulled towards other stuff. Okay, so you have your gravity relationship. The Earth is pulling on us. You're pulling on the Earth, albeit very smallly. Or, smallly a word? It is now. Okay, very little you're pulling on the Earth, but you still are pulling onto the Earth. Okay, there still is gravitational attraction that goes both ways. So we need to be able to explain the difference between mass and weight. And again, as we go through the study guide, you need to make sure that you pay attention to the learning targets, okay? The learning targets are the important part, Okay, these questions that we have for these learning targets are helpful. They're there to see if you actually can do the learning target. But if you don't sit there and read the learning target and think through, can I explain the difference between mass and weight, then all you're doing is kind of wasting time, and you're just doing problems over and over, which is a little bit helpful, but it's not the ultimate help that you could be giving yourself. Okay. A lot of you do not know how to study. I didn't know how to study until college, but this is one of the key things that you need to learn now. Studying does not mean just constantly reading your notes. It does not mean constantly just doing these questions. They do help. It is practice, and practice does help you, but it is not the end-all be-all when it comes to studying. Okay, studying is actively going through, creating new scenarios, being able to interlock and link ideas by yourself without anyone prompting you to do it. Okay, that's when you know that you've mastered the subject. When you can inspire this whole brainstorming map and do this entire thing by yourself, you don't even need these questions. You could write these questions. You know all the differences. You know how to ask trick questions, so on and so forth. That's when you know you've mastered this skill. Okay, and that's what you should be going for when you study. So again, as we go through this study guide, I'm going to be focusing not only on the questions as we get to them, but also the learning target. Okay, when you look at the learning target, when you read it, what are some things you associate with? What are some ideas that come into your brain? These are the important parts when you're studying. If you cannot do any of that when you read the learning target, that is priority number one, that you then go back to your notes, you then watch a YouTube video, you then go Google whatever you're looking for, and you get to that base level of knowledge, the DOK1, knowledge of the thing, before you can start to build with that knowledge. And we care about building with it, but if you don't have it to begin with, then you can't build with it. And that's what studying is, okay? Figuring out where you're lacking in your knowledge, figuring out where you're great in your knowledge, and spending time where you're lacking to be able to build up to be good with it, okay? That's what we're looking at. So, first learning target. I explained the differences between mass and weight. We know that mass deals with matter, weight deals with gravity, and we look at these questions, and we should be able to answer them no problem. First question. What is the weight of a 27 kilogram bicycle on Earth? Okay, so key things, first and foremost, here we go, kilogram. Okay, that kilogram is a dead giveaway that this is our mass. Okay, so this is our mass right there, 27 kilograms. It says kilograms. Kilograms is a unit of mass, therefore that is our mass. Okay. So, 27 kilogram bicycle on Earth. Why does that matter? Well, each planet has their own gravity, okay? So, in this case, G Earth is given to us as 10 meters per second squared. Now, this unit right here, okay, meters per second squared, we have to be able to identify each unit and what they mean. So when we look at meters per second squared, we know that this is a unit of acceleration, okay? Meters per second squared, that's acceleration. Do not get it confused with meters per second. That is velocity, okay? So velocity is equal to meters per second. Okay, acceleration is equal to meters per second squared. These are things that we've learned, but you may forget over time. Okay, do not get these mixed up. Velocity is not the same thing as acceleration. Remember, acceleration is the change in velocity. Okay, it's the slope on the velocity time graph. So you have your velocity is meters per second. Your acceleration meters per second squared. So when we look here, 10 meters per second squared, we know that is our acceleration due to gravity. Okay, so we are dealing with weight first and foremost. So the first thing we should do is write out the equation for weight. Weight is equal to mass times gravity. Remember, this is a derivation of the force formula, F equals ma, Newton's second law. This formula is essentially F equals ma. Weight is force due to gravity. Mass is mass. And g is our acceleration, meters per second squared, acceleration due to gravity. This is literally F equals ma. W equals mg. Okay, we plug it in. We have our weight. That is what we're looking for. Okay, so our W is our question mark. Our mass is 27. and our G is 10. So all we do is come down here and plug it in. W is equal to 27 kilograms times 10 meters per second squared. Beautiful. Do your multiplication. That's all that we need to do. W is then equal to 270. And since weight is the same thing as force, our units are newtons. So we do this. We have our answer, 270 newtons. Looky here, 270 newtons. So our answer is D. Okay? Notice, I did not look at these answer choices at all until I was matching my answer to it. I didn't look here. I didn't think of 0.37. I didn't think of 10. I didn't think of 2.7. All I did was I worked it out myself as if it was a constructor response, as if it was open-ended. Do not let those answer choices confuse you when it is clearly a math problem. When it is a math problem, you do the math. If that answer is not one of the choices, you know you did your math wrong. But if it is there, I mean, this is a simple 3-variable thing. W equals mg. We've done this plenty of times. You plug it in, you find your answer, you match it up. You do not worry about the other answers, okay? Do not confuse yourself. All right, moving on. Unlike mass that remains constant, weight of an object blank on other planets. So the key thing with this question, it says unlike mass. So this is saying, hey, you know that mass? Yeah, you know it? You know how it, remains constant? And if you didn't know that mass remains constant, well, here we are. Unlike mass that remains constant, oh wait, mass remains constant? Well, now I know, and maybe, just maybe, there's another question on the test, or the study guide, or something along the case, that's going to be important, that it's testing that. And here it goes, they literally just gave it to us. Unlike mass that remains constant. If I didn't know that, well, now I do. Look, I learned something new just by reading this question. Hopefully you already know this, but if you get to a test and you forget everything, because some of you do forget everything, use the test. They give you clues. Is this a clue for this problem? No, it doesn't matter. The problem can literally start right here, and that could be the problem. It would be the same exact question. Weight of an object blanked on the other planets. Then it becomes a fill-in-the-blank problem. Doesn't matter. It's giving you this first phrase to give you a little wink, wink, nudge, nudge. Hey, you know this? And if you don't know it, you take it and you run. Okay? They're not going to give you something wrong. They're not going to flat out say something wrong. So here we go. Unlike mass that remains constant. Great. Weight of an object blank on other planets. Okay, weight. Here we go. W equals mg. Weight. It deals with mass and with gravity. And it just says mass remains constant, so we don't want to look at the mass. We only want to look at gravity. So weight is going to do something based on the gravity. Well, on other planets, your gravity changes. So weight of an object blank on other planets. Well, it either goes up or goes down, depending on the gravity. So the answer is D. It changes. Okay? There we go. What is the acceleration due to gravity? Acceleration due to gravity. That's our G. Okay? On a where planet, okay, that's a typo. On a planet where, in its, whatever, we care about the number. Okay, the words are a little jumbled, but we care about the number. 67 kilograms. We know that's our mass because of kilograms. Astronaut weighs 154.1 newtons. Okay, we know about our newtons. So we have weight is equal to mass times gravity. It's saying what is the acceleration due to gravity, so we're solving for G. So we just come in, we isolate G. G is equal to W over M. If you absolutely need to, you can do the triangle weight is equal to mass times gravity, so on and so forth. You cover up gravity, you're left with weight over mass. If you can't do the algebra, remember this is a way to figure out the rearrangement. Okay, so we just plug it in. G is equal to our weight. Well, weighs 154.1, so 154.1 newtons. Okay, over our mass, which is 67 kilograms. Okay, and then I don't have my calculator here, so I'll get my phone. You just do the math. Okay, 154.1 divided by 67. is equal to our g, and our g is 2.3, and here we go, 2.3 meters per second squared, done. Okay? Now, what is the mass of a 25 kilogram suitcase on Jupiter and on Mars? So, now, this is asking, what is the mass? Alright, here we go. What is the mass? And then, not only do we have the mass there, it gives us a number, and that number has a unit of kilograms. Well, what do we know about the unit kilograms? Well, kilograms, we said over here, was our mass. So this is our mass. And, based on this phrase right here, look at this. Woohoo! Look at this phrase. Look how we can now use something that even if we forgot, we can use it that we saw on an earlier question. Okay? This question has already been done. We have already seen that unlike mass that remains constant, well, here we go. What is the mass on different planets? We just learned, if we didn't know already, which we should already, this should be a really easy question. But if you're in the point where you just forget everything, here we go. Look. They told it to you in an earlier question. You got to use your test-taking skills. Will this always be the case? No. No, it will not be always the case. You're supposed to know this already. But if it works, it works. Sometimes there are clues on the test, okay? So this is one of those times. Will it be like this on every test you take? No. Will it be like this on the test you take tomorrow? No. Well, maybe. I don't know. Okay? You'll never know until you're actually there. But let's take this. Let's run with it. Unlike mass that remains constant. What is the mass on different planets? Okay, mass remains constant. Well, here's our mass, 25 kilograms. Guess what? If it's Earth at 25 kilograms, that means it's Jupiter 25 kilograms, and that means it's Mars 25 kilograms. The mass doesn't change. It remains constant. It's talking about how much matter you have. The matter is the same. The gravitational pull is what changes and changes your weight. So when it asks what's the mass, and it gives you the mass, well, that's the mass. Don't make it harder than it is. All right. Fill in chart below. Well, this might have been helpful earlier, but we'll do it now. Okay, here we go. Weight, gravity, mass. We know this. Weight is equal to mass times gravity. Symbol for mass, M. Symbol for gravity, G. Symbol for weight, W. Woo, those were hard. Okay. Now, definition. This is amount of matter. So that's matter present, we'll say. Sure. Acceleration due to gravity. That's the force grav. Nope, I lied. I'm backwards. One too early. Force grav's down here. Force grav. Okay, and this is A, right? It's F grav. Remember, F equals ma. Okay, so if this is your F, this is your A, it's the acceleration, change in velocity downward. Okay? So that's our acceleration due to gravity. Our unit for mass we know is kilograms. Our unit for acceleration is meters per second squared. The squared is vital. That little 2 is vital. And weight, we know our unit is newtons. Constancy, does it change? No! Unless you get rid of matter, it's not going to change. Acceleration due to gravity? Yes, it changes based on the gravity. And therefore, since W equals mg, if g changes, W must change. It must. It absolutely has to change. Okay? When you have W is equal to mg, that means it is dependent on these two variables. If one of these two variables changes, then your product will change. Since W is your product, and we know acceleration due to gravity can change, we know weight must change. If all three of these were constant, then we would not have a formula for it. There would be no use. It would just be weight is always this. Okay, but weight definitely changes. Either your mass can change if you get rid of your matter, but when we're talking about it, we don't really care if it changes, but we'll put that as a little caveat. Yes, if you lose matter. Okay, So when people are like, oh man, I gotta lose weight, I gotta go on a diet. Well, the gravity of Earth isn't changing, but their matter might. They might lose some matter. But that's not really the case for an instantaneous thing. You don't instantaneously lose mass, okay? You can lose mass, you can definitely gain mass, but you don't instantaneously do it, so we don't really care. We're going to say no for most of the time, okay? It's yes if you lose matter. Acceleration due to gravity is yes when you change planets. You know, you're constantly going to Mars. And so weight is dependent on both mass and gravity, so it will change. So here we go. How do we feel? Well, I can solve the problem and explain it to others. Whew! I sure hope I could. There we go, first page. And we're going to draw a little smiley face because we're feeling good, off to a good start. We are off and running on the first page, our first learning target. Alright, questions over the first learning target. Explain the difference between mass and weight. So stuff can only change with matter being involved for solution. I don't think that sentence makes sense. Try again. I have no idea what you're asking. Try again. I honestly don't know what you're asking, so I can't answer it. Alright, we're moving on. Page 2. Alright, learning target. And again, we're starting with the learning target. Okay? I can relate falling objects to gravitational force. Okay, so we're looking at force grav here. What do I need to understand in order to be successful on this problem? Well, like I said, when you read the learning target, you need to talk about it. Gravitational force, we know, is a free body diagram. It is our force going down. Force grav is also equal to our weight, so we can say is equal to W. Alright, well, the constancy will change if matter is involved. Constancy... Do you mean consistency? Like, are you talking like... If matter's changing, okay, so like, say I went on a diet for 3 months, right, and I lost 20 pounds. Well, the gravity didn't change. Okay, I'm still on Earth. So that means I lost matter. Okay, that's the only way that I can lose weight on Earth, is to change your matter. Now, your matter doesn't change instantaneously. Okay, but, you can change your matter, absolutely. Yeah, you gain weight, lose weight. That's what we mean. When we say we gain weight or lose weight, we're talking about our matter changing. But in the case of, like, these questions that are like, say you're on Earth, and then all of a sudden say you're on Mars. No, your matter's not going to change like that. If they say you're on Earth, and then only half of the matter went to Mars, well then, yeah, your mass would change. Okay, but ultimately, when we're looking at these problems, mass typically doesn't change. Mass stays the same, but in real life, yeah, your mass is what changes. Okay, that's the amount of matter you have. Okay, that's what changes when you're either losing or gaining weight, because like we said, we don't leave Earth, and Earth's gravity stays there. Okay, so where were we? Objects to gravitational force. Okay, gravitational force is our weight. When it falls, that's pulling on it. That is then leads into our force is to mass times acceleration. This force goes there, which means we will end up with an acceleration. Okay, that's what I know so far. Now, let's see if that's knowledge is what is being asked about. So, suppose a ride at an amusement park starts at rest and is in freefall. Okay, freefall means the only force acting upon it is gravity. Okay, what is the velocity of the ride after 2.3 seconds? Okay, what is the velocity of the ride after 2.3 seconds? Well, that's a time, so that's our time. Okay, we know it's in free fall, so we have our force, grav, and we know the acceleration due to Earth is going to be 9.8 or 10 meters per second, depending on who's asking. So I have my acceleration and I have the time. I know that acceleration is equal to velocity over time. So if I rearrange that, velocity is equal to acceleration times time. Okay. So it says, what is the velocity? This solves for velocity. We take our acceleration, which is 10. So velocity is equal to 10 times 2.3 seconds. 10 times 2.3 means we have meters per second squared. Let's see. Let's move over here so I have more room. If I have velocity is equal to acceleration times time, velocity is equal to our acceleration, which is 10 meters per second squared, times, this was 2.3 seconds. Our velocity is going to equal 23, and we know it's velocity, so it's meters per second, but we can see if this seconds times meters per second squared, this second's going to cancel out one of these seconds, so we're left with one more second. So 23 meters per second. We move back over. We look at our answer choices, and lo and behold, we have an answer choice of 23 meters per second. There we go. So when it's in free fall, the only force acting upon it is gravity. Okay. Now, eventually, air resistance will become a thing. That's when we reach terminal velocity. But if it just says it's completely in free fall, the only force that we care about is gravity. Okay. And there we go. We found our velocity using our acceleration. We know it's velocity over time. And we rearrange so velocity is acceleration times time. And we solve for our velocity using the formulas that we learned from last unit. There we go. We're done. Got it. Okay. Draw a free body diagram illustrating free fall. We've done that plenty of times. Free fall, only force acting upon it is gravity. Woo! Going. What is the acceleration on an object in free fall on Earth? Okay. Well, if the only force is acting on it is gravity, we know that the acceleration due to gravity is 10 meters per second or 9.8 meters per second, depending on who's asking. Okay, if they want you to round or not. The state of Georgia for our big old test uses 10, so that's why we keep using 10. Okay. If an elephant and mouse fell off a cliff, who would reach the ground first? We did this. Well, okay. We didn't drop an elephant or a mouse or anything alive, but we did this with a golf ball and with a ping pong ball. Okay, we dropped them. One was way heavier than the other. We dropped them, and they fall, and they actually reach the ground at the same time. Galileo, I see you, bud. All right, and here we go. We got 2 more questions for this. A ball is thrown straight up in the air. Which statement below most accurately describes the motion of the ball at its highest point? Okay, again, test-taking skill number 1. Don't confuse yourself by reading the answers. Read the question. Stop. Think about it. Use your brain. Trust yourself. A ball is thrown straight up into the air. So here we go. We've got our guy. I'm the best artist in the world. He throws a ball. It goes up. We have a ball up here, right? He throws the ball up. It goes up and eventually comes back down, and he catches it or something. Which statement below accurately describes the motion of the ball at its highest point? Well, let's think about it. If you have your ball here, it's going to travel and then eventually it'll hit a highest point, and then it will travel back down and hit the ground again. Okay, so it goes up and then goes down. Okay, I'm a beautiful artist, I know. You don't have to tell me. Okay, so at the highest point, we know that it stops. It has to. If it's going up, it's either going to keep going forever, or it's going to come back down. And since there's gravity here, it's going to come back down. But if it's going up, that means at some point it has to change direction. At some point, if you are going this direction, for you to all of a sudden start going this one, you have to stop. So we know it's going to stop. So let's find the one that says it's going to stop. The ball has no speed. Well, stop is equal to no speed. So, okay, that sounds good. A ball has no speed, but accelerates due to gravity as it changes direction. Okay. The ball has no speed and does not accelerate since it's momentarily stopped due to gravity. Okay. The ball has speed as it changes direction. Okay. Here's where you lose me. If the ball is moving, so moving up and then it comes back down, at some point, even if it's just a very short amount of time, it has to stop. Right? To change direction, you have to come at some point to a complete stop. So that's out. I'm done. Nope, it has no speed. If it stops, it has no speed. The ball is a no, I'm done. I'm not even reading the rest of it. Okay? So, the ball has no speed. This is what I'm left with, A and B. So, the second part of the answers is what I have to now try to look at. The ball has no speed, but accelerates due to gravity. Accelerates, keyword accelerates, due to gravity as it changes direction. The ball has no speed and does not accelerate. Does not accelerate since it's momentarily stopped. Okay, if it's completely stopped. Okay, due to gravity. All right, let's look here. I'm going to draw a diagram. Ball goes up. Here's my ball at its highest point. Okay, so ball at its lowest point, or let me draw two here. Let me do two. Let me do a ball here being thrown, and then a ball here at its highest point. At its highest point, ball being thrown, it's got gravity going down, and it's got a force app going up. Okay, you throw the ball, you apply the force, it goes up. That force applied is larger than your force gravity. At some point, that force applied is no longer there. So now all we have left is our force gravity. Okay? Now, if you look at the net force here, remember I think of it like a tug of war. Applied force wins. There's a net force going up. Okay, so here our net force is going up. If there is a net force, we know that there's an acceleration. And over here, we have no force going up, but we have gravity going down. So the force net is going down. And if there's a force net, again, we know there must be an acceleration. So coming back here, there must be acceleration. So here we go, A. The ball has no speed, but accelerates. And we can work that out to look here at the very top of the of its trajectory. It has a force gravity, meaning it has acceleration. Since it's going down, it would technically be negative acceleration, but acceleration is acceleration, so it accelerates due to gravity and changes direction. We're done. Woohoo! Alright, so that was a lot of words for saying the answer is A, but remember, going through these problems, the correct answer is not the most important part. Being able to work through them, connect things that we've learned in previous units, and being able to work through the theoretical thought experiments is really what's going to serve you better, not just on your tests, not just on standardized tests, but being able to go through life. If you know physics, if you know the basics of physics, you're going to make your life a lot easier, okay? You're not going to struggle at things that some people struggle at, like how do I get this lid off the jar, okay? If you know basic physics, you know the tools, you know how to apply leverage, so on and so forth, okay? So it's going to help you throughout life. So we're on the last one. If a baseball is thrown into the air, then starts falling for 5 seconds, what is the acceleration at 3 seconds? Well, okay, same drawing, okay? We have our baseball. It is falling. It's falling. What's the acceleration at 3 seconds? Well, the only force acting on it is gravity, and we know the acceleration due to gravity is 10. So it doesn't matter what time it is, the acceleration is 10. Okay? There we go. So that learning target is done, and we can move on. Alright, how does it have no speed but acceleration? Good question. Okay, that comes back to our force applied. Our force applied, we had a force net of up, meaning our acceleration was up, right? If your net force goes up, you have an acceleration. That acceleration goes up. But as soon as you let go, the very instant you let go of that ball, you are no longer applying a force to it. All right? You apply the force as you throw it. Your hand is applying the force, but as soon as it leaves your hand, you are no longer applying a force to it. Okay? So remember, these are not motion diagrams. These are force diagrams. So here, the ball is in your hand. Here is the force diagram for literally any time after the ball leaves your hand. The split second it stops touching your hand, this is the only force diagram on it. We'll have some air resistance and so forth, but ignore all the air resistance. This is literally the entirety of the force diagram for the entire arc of it flying. As it goes up and back down, your force diagram looks exactly the same. Okay? Now, this force diagram of when it's in your hand, you're applying the force. Your force applied is greater than the force gravity, hence how the ball goes up. The more force you apply, the higher it goes. If you just apply a very small amount of force, it will not go very high before it comes back down. Okay, so you apply that force, it gives it a velocity, and the ball moves up. Now, as soon as it's moving up, okay, so here we have our ball, it's moving up, okay, the entire time the force diagram looks like this. That means it's having negative acceleration the entire time. So we had a positive and up acceleration when it was in your hand. As soon as it leaves your hand, gravity is constantly pulling that ball down. Okay? Now, that acceleration based on the force up determines how high it goes. The more acceleration, the bigger force, the more acceleration, the faster velocity you'll achieve. But as soon as it leaves that hand, you no longer have that force applied. You no longer have that acceleration as it's going up. That means it has velocity going up, it has motion going up, but the acceleration is constantly slowing it down. That acceleration is in the opposite direction. It's constantly slowing it down, and eventually force gravity, the acceleration due to force gravity, will overcome the velocity attained when you had your force applied. As soon as it equals that force applied, okay, as soon as it gets rid of all that velocity, it's going to stop. Okay, and then it's going to start falling. But when it stopped, from the very time it leaves your hand to when it stopped to when it hits the ground again, the entire time it has gravity acting on it. And the entire time, the only force acting upon it is gravity. Okay, so the entire time the ball is moving, it looks like this. That is your force diagram. Is that the motion diagram? No, it's the force diagram. And the force diagram is necessary, and it means a lot because we have our net force. And if we have a net force, if we have an unbalanced force pair, in this case, we have one force. It's not even a force pair. That means we must have acceleration. Okay? There we go. We got it. Science. You best believe I can explain it to others. All right, moving on. Next learning target, number 3. I can analyze and interpret to identify the relationship between mass and the gravitational force for falling objects. I can analyze and interpret data. We see that word a lot. That means you might get data. You might get a data chart. Here's a data chart right here. You might get a spoken thing or a written scenario that tells you about what they notice, okay? And then they give you some numbers. And anytime they give you data, you have to be able to interpret what that data is going to be, okay? To identify the relationship between mass and gravitational force for falling objects, okay? So we know that gravitational force is dependent on mass, and that's what we're looking through. Here we go. Let's dive in. What do I need to understand? Well, we need to know mass and gravity, okay? A skydiver dives from an airplane. Okay, I'm getting rid of my ball over here. A skydiver dives from an airplane. The amount of air resistance she is met with is measured at each second following her jump. Now, we have our air resistance. We have our air resistance, okay? That is directly into there. She's measured each second, okay? Second in time. That's measured there, okay? And then we have our skydiver, okay? Our skydiver has a weight. That's measured there. Okay, so the skydiver's weight, look, 500, 500, 500, 500. It does not change. Her weight is the same the entire time. Okay, so we are looking at time. It counts up 1, 2, 3, 4, and air resistance. Time 1, 200. Time 2, 300 newtons air resistance. Time 3, 400. Time 4, 500. So at 4 seconds, 500 newtons. So our air resistance is getting larger. We go 200, 300, 400, 500. The weight stays the same, and time marches on. So as time goes, you get more air resistance. The longer she falls, the more air resistance there will be. Okay? That is what the data is telling us. The longer she falls, as our time goes up, then our air resistance gets more. Now, let's see what they're asking us. Which statement best identifies her speed at each second? Okay, well, speed. Let's draw here. If we are falling, that is our F, grav, okay? And we know that we have our F, air resistance, okay? So, that is not straight up and down. It should be straight up and down, okay? F, grav, and F, air resistance, okay? Great. We have our force diagram. Which statement best identifies the speed at each second? She will be going faster at second 5. She has the fastest speed at second 1. She has the fastest speed at second 4. She has the slowest speed at second 1. So we are looking, and then eventually it wants us to predict, one of the answers wants us to predict what's going to happen at 5 seconds. So I'm going to expand my table. I'm going to know that, look here, 1 was 200, 3, 300, 3, or 2, 300, 3, 400, 4, 500. We can make an educated guess that 5 is going to be 600 newtons of air resistance, okay? That's a reasonable guess that we can do just based on the data that we were given. Which statement identifies her speed? What is speed? First off, vocabulary word for speed. We know that speed and velocity are essentially the exact same thing. We know that speed is a scalar quantity. It deals with a magnitude only. The direction does not matter for speed. So when we're looking for speed, we're looking for how fast she is going. We don't care about what direction she's going. We just care about the scalar quantity. Okay, so she'll be going faster at second 5. Okay, what determines our speed? Well, that's like asking what determines our velocity. Velocity is equal to acceleration over, or distance over time, right? Distance over time is velocity. Things that control velocity, things that influence velocity, changing velocity, that's our acceleration. We know that acceleration is equal to our velocity over our time, okay? That is our change in velocity. If we have a negative acceleration or a smaller acceleration, the smaller your acceleration, the smaller your change in velocity. The larger acceleration, the larger change in your velocity. So when we're looking at changing velocity, whether you're going faster or slower, we really need to look at acceleration because that deals with the change. Okay? Now, how do we find acceleration? Well, I don't know. Wait, I do know. Here we go. Force, force. Force diagram. We know that force is equal to mass times acceleration, and we know that it is the sum of the forces. It is the net force that is equal to our mass times acceleration. Our net force we calculate, the sum of all forces we calculate by adding together our force pairs. Gravity is going down, therefore it's negative. Air resistance going up, therefore it's positive. You add them together, one of them will win. Hint, it's gravity. Okay? The air resistance will result in a smaller net force. The more air resistance, the larger your arrow, the bigger magnitude, the less net force you have. The smaller your net force, the smaller your acceleration. That's it. We're done. The smaller net force, smaller acceleration. How do you get a smaller net force? Well, the larger your air resistance, the smaller your net force. 200, 300, 400, 500, 600. She is having a smaller net force the entire time she falls. The entire time she falls, her net force gets smaller and smaller and smaller and smaller. Okay? If your net force gets smaller and smaller and smaller and smaller, your acceleration will get smaller and smaller and smaller and smaller. So, let's look based on that knowledge. She has the slowest speed at second 1. Here we go, second 1. Okay? Now, that is when she just started out. She has a big force grav and a small, so that's second 1, right? A small air resistance. That means her net force is very large in the negative. Okay? She has a very large acceleration going down. But she started at 1 second. So she started at 0. So if she starts at her speed is equal to 0, and then she has an acceleration going down, well, if you started at 0, it doesn't really matter how large your acceleration is going to be. You started at 0. It's still going to be kind of a slow speed. Now, she has the fastest speed at second 4. Okay. She has the slowest speed at second 1. Okay. So these are in direct opposition to each other. Slowest speed at second 1, fastest speed at second 1. Well, we know that at second 0 she had no speed. So it doesn't matter what her acceleration is. We know that her acceleration is keep going down. So there's no way she can have the fastest speed at second 1. If you started at 0, there's no way that 1 second later is your fastest speed. Okay, so we're going to eliminate that. She has the fastest speed at second 4. Okay, so she constantly is falling. Now, her acceleration is getting smaller each time, but every time it's still negative. So she's still having some acceleration down. So she is getting faster and faster and faster as she goes. Okay, so fastest speed at second 4. She will be going faster at second 5. Okay. Well, we're given our weight right here, right? Here we go. Weight is equal to force grav. That is equal to 500 newtons. Okay. Our air resistance. Imagine these are straight lines. Okay. Our air resistance at second 4 is 500 newtons. That means we're at terminal velocity. There's no net force. So, at second 4, there is no net force, meaning there is no acceleration. If there is no acceleration, that means she will not be getting any faster. So, she cannot get any faster than she is at second 4. So, A is gone. She will not be going faster at second 5. So now we have the fastest speed at second 4 and the slowest speed at second 1. Okay. Now, this question gets a little confusing. Here we go. We eliminated 2 questions. Now we have, or 2 answers. Now we have 2 answers that theoretically at first glance make sense. The slowest speed at second 1, she jumped out. 1 second later, she had a large force down, but she started at 0, so therefore that should be her slowest second. And she has the fastest speed at second 4. Well, we know 4 is her terminal velocity. So, we're at a point where if you get to this on a test and both of them make sense, you can either sit here and spend a lot of time, and I've already spent a lot of time on this problem. You can spend a lot of time trying to figure out what's going here, or you can get down, eliminate your 2, and then just guess and hope you have a 50-50% answer, or a 50-50 shot. Okay? And ultimately, I mean, this one has kind of stumped me. She has the fastest speed at second 4. Yeah, that's her terminal velocity. 500 down, 500 up. She has no more acceleration. She cannot get any faster than that. That should be the fastest that she can go. So she has the fastest speed at second 4. Okay? She has the slowest speed at second 1. That should also be the case, because she jumped out. Now, the one that I feel way more okay about, okay, is C. So I'm going to go with C and hope that I'm correct. I'm about 90% certain, so I'm going to go with C. And then I would just move on, okay? There's no point, if you're on a test, there's no point spending this much time on a problem. If I had time at the end, if I had extra time, I would come back and argue this with myself again, okay? But I've argued with myself for a good 5 minutes. That's way longer than you should ever take on a problem about this. And I'm pretty sure that I'm going to go with C. She has the fastest speed at second 4. That's where I'm going to go. Okay? Now, where do we get these questions? Good question. You didn't ask it, but good question. Where did we get these questions for your study guide? Well, they come from past standardized tests. We don't make these up. Okay, we take these from test questions that have been released already. So this one might be from one of the New York tests or the Georgia test or another state standardized test. So this, I mean, there were students that saw this question on a standardized test, like you will see on the EOC. Okay, and they have to work through it. They have to be able to apply what they know. I'm sitting here, I'm applying. I'm fairly certain fastest speed will be at second 4. Now, doesn't air resistance slow you down? Eventually. Yes. Eventually. But what matters is the direction of your acceleration. As you go through here, you care about your net force. Okay? Your weight, that's our force grav. That's going down. Okay? 500 newtons. That is a net force of 300 down, net force of 200 down, net force of 100 down, net force of 0. So while these are technically slowing you down, they're not actually slowing you down. They're just decreasing your acceleration. Remember, acceleration is change in velocity. It is not your velocity. Acceleration is not your speed. So it is changing your acceleration. Your acceleration is getting lower to at the point where 4. Your in terminal velocity, your weight, and your air resistance is they both cancel out, meaning you have 0 acceleration, meaning you will not be getting any faster. Then, if we can go ahead and extrapolate, if we said 5 seconds was 600 newtons, maybe she has a parachute, right? I assume she has a parachute. If she has a parachute, then air resistance would be 600 newtons. Then she would be floating upwards. I don't think that's the case either. You can't float upwards based on air resistance alone. So, 5 seconds, we extrapolated out. We now are looking at it. See, we had time. We came back with a different mindset. We know that that makes no sense. Okay, air resistance will never push you up. It will only slow down your acceleration, not your velocity, your acceleration. So, we know that's out. So, again, after looking at it again, I'm going to go with the fastest speed at second 4. But she also has the slowest speed at, I don't know. That one's confusing. They were mean whenever they gave these to students. Woo-wee. Okay, the force of air resistance is increasing, so you slow down, right? No. You just lower your acceleration. Acceleration and velocity are not the same thing. Okay, if we have time, we'll come back and look at this. I'm moving on. All right, this one is a little hard to read. Let me draw over it. So this is our sun. We go up to a planet, over to a planet, down to a planet, and over to a planet. And then this is 1, 2. Oh, that didn't work. 2, 3, and 4. Okay. Scientists observe a distant star and 4 planets that orbit the star. Okay, here's our star. Here are 4 planets that orbit it. They determine the 4 planets have different diameters, but approximately the same mass. So they're all the same mass. Which planet has the least gravitational attraction to the star? Okay, what determines your gravitational attraction? 2 things. 1, your mass. 2, the distance away. Well, the star is the same mass because it's the star. It doesn't change. The planets are all relatively the same mass. So at this point, it doesn't matter. Okay, they are approximately the same mass. That's what we're going with. They have the same mass. It doesn't matter. So the second thing is distance. Okay, so we have distance. The one that is closest would have the greatest gravitational attraction. We're looking for the least, so we want the one that's farthest away. Well, 1, 2, 3, 4 is the farthest away, so that is our answer 4. Okay. It says the least gravitational attraction to the star, that is the one that is the furthest away. It has the least gravitational attraction. Okay, there we go. Cool. Moving on. Alright, if Jupiter and Earth were the same distance away from the Sun, which planet would have a greater gravitational attraction to the Sun? So they're the exact same distance away. So, gravitational attraction depends on 2 things, mass, distance. Okay, if they are the exact same distance, you get rid of distance, you're left with mass. Jupiter has way more mass than Earth, so Jupiter would have the stronger gravitational attraction. Find the one. Jupiter because it has a larger volume. Nope. Earth. Nope. Jupiter because it has a larger mass. There you go. Got it. Okay. So we spent a lot of time on this one. We can make it up quick on these type of questions. Do not spend longer than you have to. If you know it's the exact right answer, answer it, move on. A person that weighs 150 pounds on Earth might only weigh 95 pounds on the moon. Why is gravity stronger on Earth than it is on the moon? Now, fun fact, tangent, remember, pounds. Pounds are a unit of weight. That means pounds are a unit of force. Pounds per square inch. Okay? That is a unit, PSI. Pounds per square inch. You might hear that. That is a unit of force. It is not a unit of mass. So we're looking at our force. Well, weight, force. Makes sense. Why is gravity stronger on Earth? Earth has more mass. There you go. That's it. Earth has more mass than the moon, therefore it has more gravity. And we're done. Okay, so the only problem we had was this one right here. We know it cannot be A. We know it cannot be B. I'm fair, you know, you look at C and D. If you can't actually figure out which one is 100% the correct answer, you find the one that you most agree with. You go with that one and you move on and you come back later if you have time. Okay, test taking skills. Do not waste all your time on one question. They all count the same. Except for constructed response, which count more. Okay, so you do the one that you think is the most correct and you move on. Cool. So these 3 are relatively easy right here. And we're done with page 2. Moving on to page 3. There absolutely will be constructor response. What is going on? Computer's making noises at me. There's absolutely will be constructed response, and oh, that was my watch. Emergency service. Hold on. What in the? My watch just freaked out. This problem with smartwatches. Sometimes they're not so smart. I don't know. That was weird. Just started playing a siren at me. Alright, so there will definitely be constructor response. It's very odd. Alright. My watch has never done that before. Learning target. I can describe the effect of terminal velocity on the free fall of an object. Okay, terminal velocity. We know terminal velocity is when your air resistance and your gravity are equal. There's no net force, therefore there's no acceleration. Therefore, you are the fastest you can go. The diagram shows the force acting on a skydiver. Label the forces known as K and J. Okay, J, that's our weight or our force, gravity. Okay. That is our air resistance, and we're done. Moving on. You can label it force. Force, air resistance, far. Okay. When an object reaches terminal velocity, it has reached the lowest speed. Its speed is 0. It's reached its maximum speed. Acceleration is 10 meters per second squared. Now, this one sounds right. Acceleration is 10 meters per second squared. But that is not the case. If it is terminal velocity, we know there's no net force, there's no acceleration, that one's out. Speed is 0, out, out, and it is the maximum speed, so our answer is C. Okay? Guys, there's always constructor response. Stop freaking out. Yeah, it sounded like a cop siren because it was giving me an emergency alert. So it was like, hey, look at me. That's why it sounded like a siren. If a person A's parachute is larger than person B's parachute, who will fall faster and why? Okay, so larger parachute, more surface area. More surface area, more air resistance. So A has a larger parachute, more surface area, more air resistance. The more air resistance you have, the smaller acceleration you will have. The less air resistance you have, the greater net force down, the greater acceleration you will eventually be going faster. So who's falling faster? The one with the smaller parachute, B. Person B, because the parachute has less surface area. There we go. We got it. Done. Okay. When a skydiver reaches terminal velocity, the force of gravity equal to... Alright, here we go. Draw it out. Skydiver. Force grav is equal to 250 newtons. Beautiful. And the force of the air resistance, here we go. Air resistance. Force air resistance is equal to 250 newtons. Okay? That means our force net is 0, right? 250 up, 250 down. They cancel each other out. Force net is 0. Well, nope. And we're done. That was the answer. Got it. Look at us. We didn't even know that's what they were asking. We just know these things already, and that question becomes very easy. Boom. Questions over terminal velocity. What do you mean diet water, guys? It's actually lemon water. Get it right. Alright, and we're done with AKS 8C. So we are done looking at mass and gravitational force. We are now moving on to our next one. So, let's pause here. Any questions you have over 8C, free fall, or terminal velocity, put them in chat now so I can answer them before we move on to work and simple machines and mechanical advantage. Does more net force mean more speed? Yes, in a sense. More net force means a higher acceleration. Okay? A higher acceleration. Higher acceleration means a greater change in your velocity. If you have a larger acceleration going down, then you will have eventually more velocity, right? A bigger change in your velocity. So yes, it would eventually mean more speed. Okay, but it essentially means a larger acceleration. Okay, acceleration will then lead to more speed, but it is not exactly, it's not a one-to-one. There's a step in between there. You got to go acceleration, then to velocity. So freefall always has air resistance. No. Freefall, the only force that's acting on it is gravity. Okay, eventually you will have air resistance, but when something is in free fall, okay, the vocab word free fall, it means the only force acting on it is gravity. Okay, can you explain the surface area? Yeah, surface area. Okay, you can do it right now. Take your hand like this. Go through the air. Do you even feel anything as you go through? Maybe, maybe not, as I smack my mic. Maybe, maybe not. Now, take your hand like this. Run it through the air. Do you feel something? The answer is way more than I feel going like this. That's it. As I go through here, the only surface area I have is the front of my fingers. As I go through here, the only air resistance I have is my entire palm. Okay, that is way more surface area. Therefore, it results in more air resistance. More of whatever it is, in this case my hand, is able to hit the air. The more area you have able to hit the air, the more resistance the air will put up. That's it. So, more air resistance means less speed. No, guys. More air resistance means a smaller net force, which means a smaller acceleration. If you have a smaller acceleration, you have less change in velocity. If you're already starting out going super, super fast, and then you all of a sudden pull your air, or you add way more air resistance, okay, you will just accelerate at a slower rate. You're not going to all of a sudden slow down a bunch. You're just going to accelerate at a slower rate. Okay? I tried that. I slapped myself. Well, that's your problem. Don't do that. Alright. We are moving on to work and simple machines. Mechanical advantage. Here we go. AKS8D. Use mathematics and computational thinking. Oh, that dreaded computational thinking again. It keeps popping up, guys. Keeps popping up. To identify the relationships between work, mechanical advantage, and simple machines, calculate, give examples of force distance trade-off that occurs when a machine is used. First learning target. I can describe and give examples of simple machines. Very easy. Okay, that's all we're looking at. Describe and give examples of simple machines. And here we go. We've got levers. We've got wheel and axle. We've got pulleys, inclined planes, wedges, and screws. There are 6 of them. That's it. Do you know what each of them are? Do you know what they look like? That's all you got to be able to do to satisfy this learning target. This should be the easiest learning target to satisfy out of all of them on this review. The function of a simple machine is to make work easier. I'm lazy. I want my work to be easier. However, it does not change the amount of work performed. Just because it's easier doesn't mean you're doing less work. Okay? There we go. Fill in the blank. It makes work easier, but it does not change the amount of work you do. Now, here we go. 6 simple machines and 6 descriptions. So I can describe. Here you go. Here's your descriptions. Match them to your simple machines. Composed of a rope and 1 or more grooved wheels. Well, that's easy. That one is going to be... the heck? Where's Pulley? I don't know. Fixed point in which bar rotates about. Well, we know that's fulcrum. Modifying inclined plane. Well, that's an inclined plane. Made of two round objects that move together. That's wheel and axle. Flat surface where one side's higher. That's inclined plane. Inclined plane wrapped around a cylinder. That is our screw. Okay. A modified inclined plane can also be a lever. So we're going to say that's a lever. Or a wedge. I don't know. Modified incline. Getting a little weird here. Wheel and axle, we already said 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It should theoretically be 1-to-1. Composed of a rope and more grooved. I'm so confused. Who did this? This is from an actual test, too. That's the sad thing. Okay. Is there a pulley on here and I'm just missing it? Pulley is actually G? Yeah, I feel like there should be a G. Because this is clearly a pulley. There's literally nothing else it can be. There you go. Clearly a pulley. Okay. GCA, modified inclined plane, that's a lever. Yeah, Brian, let's go with you. GCA, DFB. What was the E? Where the GCA, DFB. Is there another one down here? Alright. Like I said, the questions are not the most important part. The most important part is, can you describe what each one is? So, can you describe what a lever is? Yes, good. Screw, yes, good. Fulcrum, do you know what that is? Yes, good. Wheel and axle, wedge, inclined plane, pulley. Do you know what those are? Good. Got it. Moving on. The wheel and axle are composed of two round objects. The larger round object is our wheel, obviously, and the smaller one is our axle. Okay, just think of like a car or a cart. The largest round thing is your wheel. That's what sits there. Okay. Oh, do you guys have a different thing? Do I have an old version of this? I might have an old version. Yeah, so levers are used, to lift things, modify an inclined plane. You can push on one side, the other side lifts up. Screw is inclined plane wrapped around a post. Fulcrum is part of the lever. Okay. Wheel and axle, big wheel, small axle. They fit together. You turn the axle, the wheel turns. Wedge is two inclined planes together. This is used to separate things. Inclined plane is a flat surface that's elevated, and pulley is the rope inside the wheel, and you turn it, and it's for lifting heavy objects. That's describing your 6 simple machines, and you're moving on. Class of lever. Here we go. Label your lever. Here we have our effort. That's where you use it. This is the point it revolves around, so that's our fulcrum. And here is where the resistance goes. The load, whatever you're working on. So our fulcrum is in between our resistance and our effort, so it is a first class lever. Okay, class of lever. Here we have our fulcrum. Here is where the load goes, so that's our resistance. And here is where you use it. You use tweezers, so that is your effort. If your effort is in between your fulcrum and your resistance, it is a third class lever. And here we have our effort. Here, the wheel, we have our fulcrum. And down here is our resistance. So this is a second class lever. Okay. Now, I realize that mine is a little weird. Okay. You're saying it might be different on yours, but the important part is, can you describe and can you figure out what they are and describe them? That's what the main difference is. Okay. Why is the part of the scissors the fulcrum? Okay, a fulcrum. The fulcrum is what the lever rotates on, or not rotate, well, I guess rotates. It's whatever the lever sits on. So if you have a lever like this, the fulcrum is whatever the solid part is that it moves on. So in this case, my finger is the fulcrum. Okay, in scissors, that's what you're doing. One side is a lever. Okay, when you actually use scissors, you actually don't super move both sides. You actually only move one side. Okay, if you ever use scissors, use them in slow-mo, slow motion, you'll see that as you use them, you're actually using one side way more than the other. That's your lever. Okay, the effort that you use, the fulcrum in the middle is what it rotates on, and then the end is your resistance. Okay, so fulcrum is what the where both meet, where the lever is, and where it doesn't really move. It rotates around that point. So in this case, it's right here. At the tweezer sits on the very back, and then the wheelbarrow, the fulcrum, is the wheel, because the wheel never actually moves. Well, the wheel turns, but it connects to the middle, and that's what never actually moves. Okay, how's the wheelbarrow second class? Because the fulcrum is on the very end. You add your effort on the other end, and your resistance is in the middle. That's textbook definition of second class. If the resistance is in between the effort and the fulcrum, it's second class. Okay. The load gives you the resistance force. So while it's not interchangeable, that is, they're directly related. Okay. Okay, moving on. Oh, that's the end of the page. Next page. Page 5. Okay, there are 3 types of levers. There are also 3 types of pulleys. Okay, just like you can tell the class of the levers based on the effort, fulcrum, and resistance, you can tell what type of pulley it is based on what the pulley is doing. Okay, here we go. If the easiest one, the pulley doesn't move, so we have a little piece of rope. The rope goes up here. I'm the best drawer in the world. Don't worry about it. Okay, you pull on one side and you raise the flag. You pull on the other side, the flag goes down, right? You pull this side goes down. Okay, up here is our pulley. The pulley never moves. If the pulley never moves, we know it's fixed. That's it. Okay, fixed pulley. Now, over here, we have a fixed pulley. But this pulley right here moves. That's a movable. If we have 2 of them, well, then it must be a compound pulley. Okay, here we have our rope is attached to here. It goes down. We have a pulley here. The rope goes back up. You attach your weight to the pulley here. Okay, and then it pulls on one side, and it raises the weight. That is a movable pulley because as the weight goes up, the pulley also goes up. Okay? So we have a fixed pulley where the pulley doesn't move, a movable pulley where the pulley does move with the load, and then if you have both of them, it is a compound pulley. Okay? So you have to be able to identify your 3 types of levers, you have to be able to identify your 3 types of pulleys, and you have to be able to identify the other types of simple machines, just either based on a picture or a description. Alright, chat, load. Alright, finally loaded. What are you guys talking about? Good Lord Almighty. Okay, so being able to identify them, we should all be good at that. Next learning target, I can describe the scenarios for when a particular type of simple machine may be used. Okay, so we have our scenarios as we look through it. When would a ramp be most useful? Well, a ramp is an inclined plane. An inclined plane is just a flat surface that is used for getting an object up to the top. Here we have him pulling an object upstairs. Here we have her watering flowers. Here we have her carrying jugs. And here we have a dude pushing a box, it looks like. Well, anyway, the only one, a ramp is used to get to a higher elevation. The only one that's trying to go to a higher elevation is this guy. A ramp would very much help him. So that is A. Okay. Alright. Often, the only way to get a large piano into a house or an apartment is to hoist. What a word! That is a very good word. Hoist it through a window. Piano movers use heavy ropes attached to a simple machine on the back of their delivery truck to get the piano into the house through the window. So if it's through the window, we have our house. Okay. If it's got a window all the way up here and they're in their truck down here, I'm the best drawer in the world, they're eventually going to have the piano down here. They have to lift it up that way. That is a pulley. Good. Okay. Gina wants to make something so that she can send her clothes down to the washing machine and save herself a trip down a flight of stairs. She's lazy. Which simple machine would complete the job and use the least amount of work? Okay. She wants to send her clothes down to the washing... Down. Keyword down. Okay. Wedge is used to separate things. That's out. Okay. Lever, inclined plane, wheel, and axle. Oh, wheel and axle is not super good at changing elevation. That's also out. Here we have a lever or an inclined plane. Okay. A lever is either used to lift a heavy object or to close and pick something up. So that one's probably out, and I'm left with an inclined plane. Okay, if she just had a nice little inclined plane going down, she could throw her clothes and it would slide all the way down like a little kid at a playground. That it? That it for the page? That's it for the page. All right. Cool. Learning target done. How do we feel? All right, judging by your off-topic conversation, I think we feel good, and I'm moving on. I'm not wasting time on your social studies projects. All right, I can calculate the mechanical advantage for simple machines. Now, mechanical advantage, first and foremost, we know that mechanical advantage is equal to F out over F in. Okay, so the force, output force, over the input force is our mechanical advantage. We know it is a ratio, meaning it is a division. And since it is a ratio, there are no units. Okay, these are things we know already. So using these, this idea, no units, it's a ratio. It is our force out over our force in. We can go and solve the problems. Okay, what two variables determine the mechanical advantage of a simple machine? Okay, the two variables used are force and distance. All right, we're talking about work. Mechanical advantage deals with work, so it's force and distance. There we go. We know that machines don't deal with speed. We know they don't deal with acceleration, so those are out. That is out. We know it deals with power in a sense, but not really, because power is work over time. Okay, and so we are left with our force and distance, so we know that already. Okay, mechanical advantage can be defined as the ratio of, here we go, it's a ratio of F out over F in. Let's look. Work input to work output. Nope. Work output to work input. Maybe. Output force to input force. That sounds better. And input force to output force. Yep. Okay. F out. That's output force. There we go. That's the best answer. Output force to input force. Okay. So, which of the following pulley systems has the largest mechanical advantage? So, how do you find the mechanical advantage of a pulley? Well, we have fixed, we have movable, and we have compound. Now, these all have different mechanical advantages. Which type of pulleys are these? Well, here is a fixed, and here is a movable. If there are both there, then we know that this type of pulley is a compound, and we know that mechanical advantage is equal to the number of loops. The number of tension-bearing ropes, the number of loops. We don't care about the rope we pull, we only care about the loops. Here we go, 1, 2, 1, 2, 3, and 1, 2, 3, 4. So, C has 4 loops. It has a mechanical advantage of 4. This has a mechanical advantage of 2, 3, and 4. So, C has the highest mechanical advantage. So, that is our answer. We can move on. Okay. What's the difference between output and input forces? Force input is what you do. Okay. So, this is you. Force input is you. This is the machine. So you put force into the machine, then the machine puts the force out. Okay, so force input is you, force output is the machine. Moving on, the distance between the rower's hand and fulcrum is 104 centimeters. The distance between the fulcrum and the water is 45.0 centimeters. What is the mechanical advantage of the oar? Okay, so we have mechanical advantage of levers. Now, mechanical advantage is force out or force in, but the problem is it doesn't give us force. It gives us distance. Okay, now mechanical advantage is also equal to your effort distance. Well, let me rephrase this. We know that mechanical advantage has different formulas for each one. Okay, the one is distance of effort over distance of your resistance. Why did I write F? Distance of your resistance. Okay, so this is essentially what it is. Okay, it's your effort arm over your resistance arm. So the rower's hand is the effort because that's what he's putting in. So it is 104 over the 45 centimeters of the resistance arm. So you do that. You do 104 divided by 45. And you find it is 2.31. Remember, there are no units because it is mechanical advantage. Okay. A simple machine has an input force of 10 newtons and an output force of 100 newtons. What's the mechanical advantage? Okay, well, we know this already. Mechanical advantage is F out over F in. So mechanical advantage is equal to our output force, which is 100, divided by our input force, which is 10. 100 divided by 10 gives us a mechanical advantage of 10. That means you put in 10 newtons of force. That's the amount of effort that you had to expend, 10 newtons of force, and you got out 100 newtons of force. Okay, that is a 10 times increase on your effort. That is a mechanical advantage of 10. That is very good. It's making your work definitely easier. It's not changing the amount of work, but it's making the effort that you have to expend easier. Okay, so calculate mechanical advantage. There are way more, like calculating mechanical advantage of a lever, which we did in the rower. Calculating advantage of a screw, which is not up here. Calculating the advantage of a inclined plane, which is not up here. Okay, these are all different mechanical advantages that you need to be able to calculate. Okay, moving on. I can explain the force distance trade-off that occurs when a type of simple machine is used. Okay, so the key point here, force distance trade-off. What does that mean? Don't get scared by it. Force distance trade-off. That just means work is equal to force times distance. Okay? Work is equal to force times distance. That means the more force you have, the smaller distance you need. The more distance you have, the smaller force you need. Okay? That's all it means. You trade off. If one goes up, the other goes down. Okay? A family moving from Pennsylvania to Connecticut during the summer. The movers are using a ramp to load boxes onto the truck. The advantage of the ramp is to reduce the... Okay? So, a ramp increases the distance, so we're looking for reducing the force to make the work easier. It reduces the force needed to raise the boxes by increasing the distance the boxes moved. Yep. But let's check the others. Time, don't care about time. Work, okay, work needed to raise the boxes. Well, the work does not change. The work stays the same, so that's out. Effort needed, okay? Effort needed, that sounds about right. To reduce the distance, well, no, reducing the distance, it increases. You now have to go up the entire ramp, so it does not reduce the distance. So our answer is A. Okay? The diagram below shows a pair of pliers gripping a bolt. We have our pliers. They're labeled A, B, and then we are drawn to here. Okay, so this lines up with that part of the plier. We have A here and B here. So this part of the plier is our fulcrum. Okay? Pliers multiply the force of a person's grip through the use of leverage. For the pliers shown, A is 10 pounds. So this is 10 pounds. Remember, pounds is a unit of force. So that is our effort force. Okay? B is equal to 1 inch. Okay, what is the gripping force, or what is B? So we're looking for B at the jaws of the pliers. Okay, so we have to calculate the mechanical advantage to be able to then find the gripping force of the pliers. So it multiplies the force of a person's grip. So we know for a fact, if we put in 10 pounds, this is a first class lever. If we put in 10 pounds, if the resistance arm is smaller than the effort arm, we know, okay, that the mechanical advantage is greater than 1. And here, A is equal to 3 inches. B is equal to 1 inch. We know that the effort arm is smaller. So we know our mechanical advantage is going to be greater than 1. Meaning that we put in 10 pounds, we will get out something that is larger than pounds. So instantly, I can get rid of A. I don't have to do any math to get rid of A. Okay? Is below 10 pounds. So that means that we would have a mechanical advantage less than 1. That's not the case here. Okay, so we have to calculate our mechanical advantage. This is a lever. Okay, so our mechanical advantage is going to be our effort arm over our resistance arm. So it's going to be 3 over 1. 3 divided by 1 is 3. Okay, that is our mechanical advantage. Now, mechanical advantage is equal to our F out over our F in. Okay? If we know our mechanical advantage, which we calculated using the distance, effort over resistance, we know that's 3. We know our F in, we can solve for our F out. So that's 10 pounds. That's F out. We solve it. F out is equal to 10 times 3, right? We move 10 to the other side. That's going to be equal to 30 pounds. So there's our answer, 30 pounds. Okay? An adult and a small child are at the playground. The child sits at the end of the seesaw as shown. The adult weighs twice as much as the child. Okay, this is like our balancing beam that we started with. Okay, force, distance, trade off. The more force you have, the less distance you need. Okay, so if she is 2 marks away and something, so let's give her a mass of 1. Then where would you put the mass of 2? 1, 2. If you put the 2 here, then it would go down. Okay, we know that. If it's the same distance away, it must be the same force. So, since it's twice the amount of force, okay, twice the amount of weight, it must go half the distance. So, instead of 2 meters, it goes 1 meter. So, point C is the correct answer. Okay? 10 newtons is not equal to 10 pounds. They are not the same thing. Pounds is a different unit of force. Okay, pounds is the imperial unit of force, whereas newtons is the scientific or the metric unit of force. Okay, they're two separate things, but they are both units of force. Great, that's it. Balancing beam. That's it. We're done. Okay, now things that are not on here that you should make sure you know how to do the rest of the mechanical advantages. Okay, there's only 1, 2, 3, 4, 5 questions on here. There are 6 machines. So obviously not everything is on the review. So you need to know how to do it for all the simple machines. Okay, you need to know that it's force out over force in. The other thing that you can do is memorize all the different equations that we had for it, or you can do the distance of the effort or over the distance of the resistance, and you can find that. Okay, and then over here you have to know the force distance trade-off, right? You increase the distance to limit the amount of force you have to put in. The less force you have to put in, the easier it is. Okay, and then force distance trade-off for balancing beam. Remember, the further away from the fulcrum you are, okay, the less force you need to move it. Okay, so if you have a lot of weight, you want it close to the fulcrum. Okay, and that's it. We're done. Last minute questions, get them in. That skydiving question is harder than ones you'll probably see, unless you see it in May. I wouldn't put a skydiving question like that on anything, and I don't think any of the other teachers would. But I'm fairly confident in my answer. Let's see, where was it? Up here. Yeah, it's the best answer is C. Okay, the fastest speed at second force. She's at terminal velocity. You cannot get faster than terminal velocity. That is the last velocity you can attain. Okay, unless you add in another force, you will never get faster than terminal velocity. At 4 seconds, she's at terminal velocity. That has to be the right answer. This is the best answer there. So yeah, C. What is the formula for freefall? There is no formula for freefall. Freefall is a state of being, is when the only force acting on you is gravity. I'm not helping you with the worksheet. I'm helping you with the study guide. Will the equations to solve them be on the test? Not the ones you want them to be. They'll be F out over F in, and the effort distance over the resistance distance. But each, like the formula specifically for lever, will not be up there. Okay? Can you explain how you did the force diagrams? That was last unit. Which force diagrams? You just draw which forces are acting on them. The most force diagrams we did here was force gravity. Okay, we know gravity points straight down. We know air resistance is opposite to the way you're moving. If you're falling down, your air resistance must go up. Okay, that's the force diagram. And then you have your unbalanced force pairs. Whichever one wins the tug of war, that's the way I think about it. And that's the way your net force points. So force gravity is going to beat air resistance at all times except for terminal velocity. So your acceleration will be down. And at terminal velocity, your acceleration is 0. So because there's no net force. So I don't know what you mean by explain force diagrams. But we're just using how we do force diagrams onto the other one. Or we're using them to solve for these things. Any other questions? Yeah, it's accelerating the entire time. It's not getting any slower. The acceleration is getting smaller, okay? But the acceleration getting smaller still means that there is a... Alright, seriously? You're in timeout. Goodbye. Okay, so the acceleration being smaller does not mean that your velocity is changing, okay? So what matters is the acceleration deals with the change in velocity. Your velocity isn't all of a sudden negative. You're not all of a sudden going slower. I mean, it's not getting smaller. The acceleration requires the velocity not changing as much. So you're not getting faster in a shorter amount of time is really what it comes down to. What is the resistance when you identify the class? Oh, pulleys. No, levers. You mean levers. Okay? What is the resistance? The resistance is what the lever is doing. Okay? The work. Okay? So, the resistance deals with the actual, like what you're doing work on. With scissors, you're doing work on the paper. Okay? With a tweezers, you're doing work where you are picking something up. With a wheelbarrow, you're doing work by carrying whatever is in the barrow part of the wheelbarrow. Okay, that the load is what you're picking up or moving, and then the resistance is the force from the load. Okay, so they're almost interchangeable. They are slightly different. Okay, and that's about it. I got confused more. Wow. On what? What you get confused more on? What else we got? Is that it? We done? So, things that you should still look over before you go to bed or look over in the morning. Okay, mechanical advantage, how to calculate mechanical advantage for every single machine. You should be able to identify every single machine, not only identify what type of machine it is, but identify the class or the type of pulley. And then being able to look at work and know that work does not change. Okay, you still do the same amount of work, so you have to do the same amount of work, but you were either going to trade off your force or your distance. You're either going to do more force over a smaller distance or less force over a greater distance. Okay, you need to get that all straight. How can you identify the pulleys when they look identical? They do not look identical in any way, shape, or form. Okay, clearly one is fixed. Okay, it is not moving. If it is not moving, it is fixed. If it is moving, we call it movable. And if they have both types, then it's compound. Okay, so identifying pulleys is actually very, very easy. Does the pulley move? Yes or no? Is the pulley tied or welded or something, you know, affixed to something? If it is, then it's fixed. If it's not, then it can move. That's it. Okay. How do you tell the mechanical advantage of a compound pulley? You count the number of loops, dude. That's easy. You just count the loops. Here you go. This is what we did. You count the loops. You don't care about the... You do not care about the one you pull. You care about the rope that's in the pulleys. So, the loops within the pulleys. So, one rope, two ropes. Okay? Well, it's all the same rope. So, one loop, two loops. That's a mechanical advantage of 2. One loop, two loop, 3 loops. Mechanical advantage of 3. One loop, two loop, 3 loop, 4 loop. Mechanical advantage of 4. Okay, that's all you do. You ignore the rope that you pull, and you count the other ones. That's it. That's all you got to do to find the mechanical advantage of a compound pulley. How do you identify input force from words? Okay, if a human does the force, it's input. If a machine does the force, it's output. How do you tell if it's a loop? Look, they're within the pulleys. If it goes from one pulley to another pulley, it's a loop. Remember the pulleys we looked at in class. If it goes in one pulley and up to another one, it makes a loop. If it comes out and you can pull on it, well, then it's no longer looped. So we don't care about that one. What else you got? Is that it? Is it possible to have a larger object with an axle? If you have a wheel and axle, the larger object is always the wheel. Smaller object's the axle. Could something potentially be the wheel and then you change it into working with something else and all of a sudden it's the axle? Yes. Okay, but the smaller one, the smaller diameter is always the axle. The larger diameter is always the wheel. Okay? Alright, with that being said, we are going to bring this to an end. It is 9:48. You need to make sure that you have a grasp of all your learning targets. You need to make sure you finish the worksheet that's due tomorrow, and you need to make sure you get some sleep. Okay, so tomorrow is Wednesday. We are almost halfway through the week. We will be able to make it. What's due tomorrow? The worksheet you got yesterday. Mechanical advantage, 11 questions, due tomorrow. Pretty easy. Should not take a very long time. The reason you have that is because on the study guide, we obviously could not put all the mechanical advantages for the study guide. So you have a worksheet so you can practice the other mechanical advantages. Okay? That's why you have it. You need to make sure you do it because tomorrow on the test, you'll have to calculate more than just what is given. Okay? You got to be able to calculate them for all. All right. Goodbye.